Here we have an ACCA classic. We've got high-low method. So to review what we're doing here, we have information about activity level, which would be on the x-axis of a graph. We have total cost, which would be on the y-axis. And then we have a range of activities and some associated total costs. He's just making up some numbers here. Okay. High-low method, what are we doing? We're finding the high activity, the associated high total cost. Then we find the low activity and the associated low total cost, even if we see an outlier data point below that one. Like, for example, imagine that was down here. No. You just grab the high and the low. We ignore everything else, and we assume perfect correlation and a linear equation like this, and where that line intersects with the vertical line, that would be the fixed cost. The gradient of that line would then be the variable cost. That is the high-low method. And the solution to the high-low method will always be in the form of y equals a plus bx, or total cost equals the fixed cost plus the variable cost multiplied by the activity level. So looking at the answers right away, we can eliminate D. And if we're down to the last minute, we then have better odds with our guess. And I can look at these answers as well, and I can see that the variable cost is different for each of them. So we don't need to take it to the fixed cost level. So all we have to do now is find the high activity and the low activity. That's the high. That's the low activity, even though we have an outlier here. No, we don't want that one. We want the 400 clients. Now all I need to do is this. I know my total cost. I know my units. I can do the high, the low, the difference. And then the change in total cost divided by the change in units is my estimated variable cost. Okay, so my total cost at the high level, 40,000 with 460 units, dropping down to 36,880 with the low clients, 400 now. We can get the change, D, delta, difference, right? And that is 3120. 460 minus 400, well, that's 60. Divide one by the other, and we get our solution, 52. Okay, so that's the estimated variable cost. The answer has to be B, without even going to the without even figuring out the fixed cost. But let's just do the fixed cost since we're here working. Maybe you'll need that next time. So we know the variable cost. Let me put that up here. Let me clear out the space. Now, all we need to do is a little algebra, and if we know total cost is equal to fixed cost plus variable cost multiplied by x, okay, we can just grab either of these, the high or the low. Let's grab the high because we have the round total cost there. So the total cost would be 40,000 equals fixed cost plus 52 from before multiplied by 460 units. Okay, now if we isolate the fixed costs over here, that's simply going to be that total cost minus the variable cost. The variable cost comes to 23,920. Okay, so we subtract that from the 40,000, guys, and the solution is then 16080. That's how we would do the total cost. Guys, answer is B. Learning curve, everyone. What fun. let's do it. I know it's learning curve. How long would it take the designer to complete the sixth job? And I see this learning rate. That only goes with learning curve. Let's just review the theory, then we'll do this question together. What we're saying here is that the time per unit is decreasing due to familiarity. So if we had this as the number of units increasing, this as the time per unit. Okay, unit number 1 is going to be there. And as we make more units, the time per unit decreases. Eventually, a steady state is achieved. Okay, and it becomes a variable cost, a constant. Okay, but that's the time per unit dropping as the units increase. Okay, another way of looking at that, if we look at the total time, okay, as we start making units, the total time is going to be curving downwards. Okay, eventually it achieves again a steady state. And the question is asking us, how much time would it take the designer to do number 6? And that's not the total for 6, that's unit number 6. So what we would do then, we're going to find the total time for number 6. Assume it's right there. Okay. Then we get the total time to make 5 units. Right, we get the total time to do 6, the total time to do 5, and the difference would be the time for unit number 6. So there's a lot to do here. You need to practice this. And I'll tell you about a super cool trick at the end of this little set, okay? So stay with me. Let's do it on paper first, and then I'll tell you about the cool trick. So we're going to need to deploy the formula. This is one of the few formulas they give us in the formula page. That is y is equal to ax to the power of b. Look at this. We have some exponential growth happening. So y is the average time per unit when we're making the number of units. A, time for number 1. X, the number that we're doing, and B is this learning factor given to us as a negative 0.415. Okay, so we're going to do 2 things. We're going to do the total time to make 6, the total time to make 5. Right, and the difference then is going to be the time for number 6. Okay, now what information do we have? Well, we know that we're making some electronics, some phones, so there's a repetitive process, so our engineers will go faster as they make more of them. The learning rate goes to 15. Why do they care about number 6? I don't know. The question wants us to calculate number 6, so we've got everything we need to do. I'm going to go down a bit. I need more space. So the total time for 6, y is equal to ax to the power of b. Okay. A, the time for the first one. Did they tell us that? The first one took how long? 5 hours. Buried. Look at that. They put it like that in the sentence to make it a little more difficult. They encoded that number in words. Okay, so you must carefully read. 5 hours. Okay, so let's come over here. That's going to be 5 multiplied by 6 to the power of negative 0.415. I'm going to put this into my calculator. Okay, in my calculator, I've got a 2.377 and some more numbers there. I'm going to keep it in my calculator because now that's the average time per unit. Now the total time for 6, we have to multiply that by 6. That's the average time. Okay, so now we do 6 multiplied by the 2.377. So that will be a 14.262, the total time to make 6. But friends, I'm going to show you a cool shortcut. Right now, with this information, we can answer the question. Let me show you how. Let's come back up here. If we remember this principle, right? Time per unit is decreasing. That's going to be number 6. Okay, that's, call it 0 for now. 1 would be there. Average time per unit is decreasing as we produce more. The first one is number 5. Look at this. It can't be number 5. Now, answer C matches what we just got, 2377. I'm sorry, not C, A, 2377. There it is. That's the average time. So if we're doing 6, we're going to go faster. So it has to be a number lower than 2377. C is bigger, B is lower, so it has to be B, just from a little logic and some quick thinking and staying focused. But we can finish it now, just for practice. We can finish it. So we come back here. That's the total time to do 6, 14,262. Now we do the total time for 5 using the same formula. And this time it's going to be 5 times 5 to the power of negative 0.415. And the y is going to come to 2.564. I keep that number in my calculator and I multiply by 5 units and I get a 12,819. Total time for 5 is 12.819. Again, remember this is the average time per unit when we are doing 5 units. So 12,819, let's put that into our table upstairs. Okay, and the difference, guys, the difference is 1.443. That's the time for number 6, and answer is B, right, with a little bit of rounding. There you have it. Now, the cool way to do this is what I wanted to tell you. If you get a learning curve question like this in the exam, what you do, you copy this important information, you type it right into the scratch pad. Then you go to the navigator and go into the spreadsheet in section C. Quickly do all of this in the spreadsheet. You'll go much faster if you have to do learning curve. Then you bring your solution back into section A and you plug it in. Okay, so don't be afraid to use the spreadsheet in section C if you have to do any heavy lifting with the mathematics. For example, the exponential business, that's going to be easier in a spreadsheet. Here we have another learning curve question. And in order to do this, you need to understand the difference between 80% and 75% rate of learning. If you remember, we see the effect of the learning curve when the production doubles, if we're doing it that old-fashioned approach in the table. So if we did this, just 2 items, right? The units, we do 1, we do 2, okay? Then if we do the cumulative average time, well, when we make 1 unit, let's pretend it's 100 minutes, right? If it's 100 minutes, the time per unit for number 1 is going to be 100. Now, when production doubles, we see the learning rate in play. So that would be 0.8 multiplied by 100, so 80. So the average time per unit would be 80 minutes when we do 2. Okay? Guys, now, if the learning rate were actually 75%, the first unit is still 100 minutes. The average time per unit when we do 2 would be 75 minutes. So, guys, 75 is a faster rate of learning. That's an improvement. The guys went faster. When you understand that, the rest of it is easy peasy. So, which of the reasons could have caused the difference? Guys, which of the reasons could have made the workers go faster? Well, the number of new employees recruited was lower. Well, then we have more experienced workers. That would help us go faster. Unexpected problems were encountered in production. No way. That would make us go slower. Unexpected changes to the laws meant the company had to give them more breaks. No, that would make us go slower. So the only thing that would make the workers go faster would be more experienced workers. So guys, the answer is C.